Generally, I will say you best example for it. If you take the H2O, what is the boiling temperature of the H2O? 100 degree. If you take the ethanol, that is alcohol, what is the ethanol boiling temperature? It is 78 degrees. If you add it both alcohol and the water, what it will happen? It will form a one solution, right? One mixture. Separate out the which one? Azeotropic mixture and the pure one component. These are the some experimental graphs they have given through the fractional distillation. This H2O plus ethanol, we will call it as a minimum boiling azeotropes. Hello my dear friends, in this lecture we are going to deal with the one very important concept, that is azeotropic mixture. What are the azeotropic mixtures, sir? Okay, generally I will say you best example for it. If you take the H2O, what is the boiling temperature of the H2O? 100 degree. If you take the ethanol, that is alcohol, what is the ethanol boiling temperature? It is 78 degrees. If you add it both alcohol and the water, what it will happen? It will form a one solution, right? One mixture. If you heat that mixture, what it will happen? Instead of heating above the 100, instead of heating between the 78 to 100, it is heating, it is converting into the vapors below the temperature of 78. That type of the mixture we call it as a azeotropic mixture. So how to separate that azeotropic mixture or alcohol or ethanol solution, and how to separate the pure solvent or pure any of the one component, that we are going to see in this lecture. Before going to start our azeotropic mixture, I just want to explain you about the one distillation, one process, that is fractional distillation. You can see here, what is that one? That is a fractional distillation. See, what is the meaning of the fractional distillation and what we are going to see. First of all, what is the meaning of the fractional distillation? Fractional distillation means separation of the two miscible liquids or two miscible volatile liquids is known as the fractional distillation. If you take the one A and one B, one A type liquid, one B type liquid you have taken. Now you are added to the solution. So the one which is having less boiling temperature, that it will be separate out. Clear? The one which is having the higher boiling point, it will be in the same solution. So general example for you. Now listen, here I was taken the one pure ethanol. One ethanol and the water I was mixed. This alcohol and water I was mixed. This has become the solution, right? Now how I can separate the ethanol and the water? How I can separate the ethanol and the water? Now you see, this is the ethanol solution. This is total what? Ethanol solution. This is water and the ethanol solution. If I was heated this one, now ethanol boiling temperature is 78 degrees. Now H2O boiling temperature is 100 degrees. When you are giving the heat, when at the 78 degrees Celsius, when the heat has been reached, what it will happen? From this water and the ethanol solution, pure ethanol vapors will become. Pure ethanol vapors will be what? It will be evaporate from the liquid solution. See here, whatever the vapors it is coming, that is of the pure ethanol vapors. Done. Then when it is coming, now here we have taken the one condensate. Here what we have taken? This is a one condenser. Now what is the meaning of the condensation? Converting the gas into the liquid, right? Converting the gas into the liquid. This is a condenser. One condenser with the whatever the gas it has been evolved. Now we will send it to that condenser. What that condenser it will do? It will cool out. Here whatever the temperature we have given here, the 78 degrees. Now when this gas has been passed to this condenser, what it will happen? Its temperature will be decreased. It's that gas temperature before it is a 78 degrees. Now what happened? It has been decreased to the how much? Now let's suppose it has been decreased to the some 25 or something. Then what happened? Whatever the gas it is there, it will be converted into liquid. See, when this gas has been converted into this condenser, what it will happen? It will be converted into liquid. When it has been converted into liquid, now from here the pure ethanol will be separated. All the ethanol, when it has been evaporated, now at a certain temperature, here what it will be left? Only the H2O will be left. Now here which we can collect? Pure ethanol we can collect. This type of the process we call it as a fractional distillation. Fractional distillation means two miscible volatile liquids we can separate out. Clear? This is known as a fractional distillation. This is known as a fractional distillation. Okay. Now this we have studied about the fractional distillation. Now I want to, by what I want to give you here, whatever the curve you are seeing here, whatever the curve you are going to see here, 1 minute. Now you see this, whatever the curve we are seeing here, this is vapor pressure and this is the vapor pressure and this is the mole fraction. Now this type of the curve we call it as a liquid and vapor composition curve. Liquid and the vapor composition curve. Clear? In this liquid and the vapor composition curve, now what we are going to see and how it is related with the, which one? How it is related with the fractional distillation. Now you see here, if this curves, if it is clear for you, the topic which we are going to study, that is azeotropic mixture, it will be clear for you. Now listen, here what I was doing, this is a vapor pressure is increasing, here it is a vapor pressure is increasing, means vapor pressure is increasing means, now you say me, for the one substance, if I was increased the pressure, what it will happen? If you take the gas substance, if you increase the vapor or if you increase the pressure for that gas, what it will happen? That gas will be converted into liquid, right? All the gas particles will come closer. The kinetic energy between the one gas molecule will be attract. Due to that attraction, what it will happen? Gas particles will be converted into liquid. That gas particle will be converted into liquid, right? Clear? Means as the vapor pressure is increasing, now before here, whatever the, according to the Raoult's law, this graph has kept. Now whatever the, as the vapor pressure is increasing, whatever the composition here we are having, that is only due to the, that are all are in the vapor, right? That all are in the gaseous. Now as the vapor pressure is increasing, now that composition vapor will be changes to the liquid. Now here entirely it will be in the liquid phase, here entirely it is in the gaseous phase. Means in between these two, what it will be there? In between these two, let's suppose I was taking this two, in between these two, liquid and the vapor are in the equilibrium. Is it clear up to now? Now you see, now how to read this graph? Now reading of the graph is very important. How to read the graph? Now you see, here chi A is 1. Here at the 0, chi A is 1. Chi B is 0. Here the chi B is 1. Chi A is 0. Clear? Now here at a certain particular temperature, sir, at particular pressure I was talking, not about the temperature, at the particular pressure I was talking, certain pressure I was taking. This is a one certain pressure I was taking. For this certain pressure, this is a liquid composition curve. Means, sir, I did not understand. Okay, now listen carefully. Here, what I was taking, just now we have talked about the which one? We are talking about the fractional distillation, right? No, in this fractional distillation, one component I was taking. Okay, here this is the one component I was taking. Okay, now here two liquids we are having. One is A component and one is a B component we are taking. One A component and the B component. For a particular pressure, these components A and B, we are saying that vapor pressure of the B is higher than the vapor pressure of the A. Vapor pressure of the B is higher than the vapor pressure of the A. Vapor pressure B, if it is high, means at the low temperature it will be evaporate out. Means here two vapors will come. When it has converted into the gaseous, A components will be less, but B vapors will be more. You can see B vapors will be more. In the gaseous, A vapors are less. Right? Why? Vapor pressure of the B is more. Means this component A and B, when it has converted into the vapor, B vapors are more, A vapors are somewhat less. Now here at certain pressure, if I want to calculate this liquid how much composition is nothing but how much mole fraction this A and B are having in the liquid, and how much mole fraction these are having in the gaseous. So here one point you have to remember, at this midpoint, this is a midpoint, right? 0.5. 0.5 from this graph, if we cut here, now here A component, A will be in the rich. Midpoint, left to the midpoint, which one will be rich? A will be rich. Now midpoint to the right side, here this side B will be rich. Here the B is rich, B component is rich. Now this side A component is rich. Done. Up to now, is it clear? Now you see, at this particular pressure, now this is a liquid composition curve, right? This is a liquid composition curve. This is a liquid composition curve. In this liquid composition curve, now if I draw, now how much I got? This is 0.2. So what is the mole fraction of the A here in the liquid phase? What is the mole fraction? This is liquid composition curve. If I cut it here, this is 0.2, right? Then you may get a doubt it here. You will say that, sir, this mole fraction of the A, here it is a 0.2, and here the mole fraction of the B is 0.8, you will say. But actually this is wrong. Actually this is wrong. Why it is wrong? Now you see, already I explained very clearly. What I explained? What I was explained? Now you see, this is liquid A and liquid B. Now already I said you, mole fraction of the, vapor pressure of the B is high, means in the vapor phase B will be high. Now in the liquid phase A will be high, and in the gaseous phase A will be less. Means mole fraction, what I said, if it is left side to the midpoint 0.5, A will be rich, right? A will be rich. According to this composition, if you got it as a 0.2, it means that mole fraction of the A is 0.8 and mole fraction of the B is 0.2. Mole fraction of the A is 0.2. Means this point is indicating that A is having the more mole fraction in the liquid phase. A is having more mole fraction in the liquid phase. How much it is having? 0.8 it is having. 0.8 it is having. How much B it is having in the liquid phase? 0.2 it is having. 0.2 it is having. Clear? Now at the same phase, or at the same pressure, how much mole fraction these gases are having? How much mole fraction these gases are having? For that one, what you do? You just extend this curve. Okay? When you extended this curve, now what happened? Now it will be reached to the some point. Here it will be reached. Means this point is somewhat higher than the 0.5, right? Higher than the 0.5. If it is, this point is higher than the 0.5. Now arbitrarily I was saying, this is arbitrarily. If this point is higher in the, which one? Compared to the 0.5, it is higher, right? Compared to the 0.5, it is higher. Means here the richer in the B. It is richer in the B. Means the gaseous phase, whatever the mole fraction we are having, that B will be high and A will be less. Okay? This is the liquid and the vapor composition curve. It may be somewhat make you too difficult to understand, but studying of this graph is very, very important. Clear? Now next, now comes here. Here this curve is, this is also liquid and the vapor composition curve only, but this time it is on the basis of temperature and the mole fraction. Now here what we have seen? Here we have seen on the basis of vapor pressure and mole fraction. Now this graph is on the basis of temperature and the mole fraction. Now temperature and the mole fraction, now you see how we can read this graph. How to read this graph? Now we'll see. Here, if you increase the temperature, If you increase the temperature, what happened? Liquid will be converted into vapor, right? Liquid will be converted into vapor. The same thing. This all are the liquid phase. This all are the vapor phase. This all are the liquid, and this above one is a vapor phase. Now you see, at a particular what, this is a midpoint. This is a one midpoint. What I said, for the midpoint lesser, A will be the richer. Now the midpoint right, B will be the richer. Now at 370 degrees I was talking. Now you see, at the particular temperature 370 degree I was talking. This is the which one? Liquid composition curve. Liquid composition curve. In this liquid composition curve, how much liquid I am having? Some 0.3 liquid. From this composition we got the 0.3. So if you talk about this one, here the two compositions we are having. Here the A and here it is a B. Clear? Here the A and here it is a B. Now in the gaseous phase, B is higher. Now A is lesser. This is A. Done. Now you see, what does this 0.3 is representing? Now here mole fraction of the A, but mole fraction of the A is not 0.3. What I said, left side mole fraction of the A will be I. If it is from this graph, if you got the 0.3 means actually the number of moles of A that is present, it is 0.7. Means what does it is indicating? In the liquid phase, A is having higher mole fraction. How much? 0.7 is a mole fraction it is having. B is having how much? 0.3. B is having 0.3. Now at the same composition, if I extend this graph, clear? If I extend this graph, now when I was extended this graph up to here, now this is cutting the which one? Vapor phase, vapor composition curve it is cutting. Now if I write the mole fraction here, and if I draw the mole fraction here, or if I cut the mole fraction here, how much I am getting? This side, midpoint, this side, the B will be richer, right? Now this is the vapor phase. In the vapor phase, this is 0.7. In the vapor phase, how much B I am having? YB is 0. No, how much B I am having? YB is equal to 0.7. Then YA how much I will get? YA will be 0.3. If in the liquid phase mole fraction of the A is high, in the gaseous phase mole fraction of the A will be less. In the liquid phase mole fraction of the B is less, and in the vapor phase mole fraction of the B will be high. This is the composition curves that it is saying. That composition curves are saying what? This is a liquid phase, A is high, the gaseous phase it is less. Now in the liquid phase B is less, in the gaseous phase it is high. That is only the graphs. This is about the liquid and the vapor pressure composition with the vapor pressure. Now we got this graph. Now with the temperature we got this graph. Clear? Now by this topic, now how to read the graphs if they have given versus temperature versus mole fraction, if the graph if they have given vapor pressure versus mole fraction. Now we'll see what are the azeotropic mixture. Azeotropic mixture means these are binary liquid solution having same composition in liquid and gaseous phase. In the gaseous phase and the liquid phase, its composition is having same. Means here if I take the one liquid, this is the one azeotropic mixture. Now let's suppose this is one azeotropic mixture. Okay. Now this azeotropic mixture, when it has converted into the gaseous, now this gaseous in the liquid phase and in the gaseous phase, what its composition will be same. Sir, how it is composition will be same, that I will explain through the graph. With the graph it will be clear for. Okay, now this mixture boils at constant temperature without changing its composition. Without changing any of its composition, it will boil at the constant temperature. Now you see here, very important point you have to remember. What is a very important point you have to remember? If you take any two azeotropic mixture, or if you take any one azeotropic mixture is forming through what? When the two liquids, when you mix it, both are forming one azeotropic mixture. So better example, if you want to take the which one azeotropic mixture, one A. Here let's suppose this is a one solution. This is A and this is B. This A and B formed the azeotropic mixture. What is the meaning of azeotropic mixture? Azeotropic mixture means instead of boiling at their boiling temperature, those are boiling at the below to it or above to it. Those type of the mixture we call it as a azeotropic mixture. Now you see, this one boiling temperature is, let us assume, 98 degrees Celsius. This one boiling temperature is when they are in the pure state, not in the azeotropic mixture. Let's suppose this is having the 78 degrees. Okay. Now, when the temperature has been reached to the 77 degrees only, when the temperature has been decreased to the 77, now here the vapors we are getting. Here whatever the vapors we are getting, that is of the both. Not, we cannot say that is a, we cannot say that is a B. Clear? That type of the mixture we call it as a azeotropic mixture. But what is a very important point here we are going to study. If you want to separate, this two has formed the azeotropic mixture, right? From this azeotropic mixture, now what you want to do? You want to separate out this A and you want to separate out this B as a pure. You want to separate out as a pure A and you want to separate out as a pure B. But with the simple distillation or the fractional distillation, we cannot separate out which one? Pure component and from the azeotropic mixture. This is a very important point. Sir, what is the point we have to remember? Means when the azeotropic mixture has been formed, we cannot separate out its pure components. We cannot separate out into its pure components. This A and B has formed the azeotropic mixture. We cannot separate out this A and B again. What we can separate? One we can separate. But this azeotropic mixture we can separate out. With the help of the distillation, we can separate out at least one component. Sir, how? What is the one example? General example I was taking for you. This is ethanol solution. H2O plus ethanol. Clear? These two are forming the azeotropic mixture. Done? When these two are forming the azeotropic mixture, from the distillation, what we can separate out? Either we can separate out the pure ethanol and this azeotropic mixture, H2O plus ethanol, we can separate out. Either we can separate out the H2O, pure H2O and azeotropic mixture. But H2O and ethanol we cannot be separate out. H2O and the ethanol cannot be separate out. Clear? Now this is a one key point you have to remember. So now what is the key point you have to remember? Sir, why we cannot separate out? With the help of the graphs you will understand. I will make you to understand with the help of the graphs. Now you listen. Here what the point you have to remember? An azeotropic mixture cannot be separated into their pure components, cannot be separated into their pure component. This is the one key point of the azeotropic mixture. Cannot be separated into its pure component through simple or fractional distillation. Simple or through the fractional distillation. Through the simple or the fractional distillation, we cannot separate out its two components. But during fractional distillation, what we can separate out? We can separate out azeotropic mixture and one pure component through the fractional distillation. Either we can separate out the azeotropic mixture and one the pure component. Sir, how we can separate out? That through the graph we will get. Now, before going to the graphs, now how many types of the azeotropic mixtures has been classified? Here the azeotropic mixtures has been classified into two types. Here the azeotropic mixtures has been classified into two types. First one is a maximum boiling azeotropes. Maximum boiling azeotropes. Clear? Second one is a minimum boiling azeotropes. One is a maximum boiling azeotropes, one is a minimum boiling azeotrope. Sir, what is the meaning of the maximum and what is the meaning of the minimum? See, already we have studied about the Raoult's law. In that Raoult's law, the one which obey the Raoult's law is an ideal solution. Now, the one which does not obey the Raoult's law is known as a non-ideal solution. In that non-ideal solution, we have studied about the positive deviation and one is a negative deviation. In the positive deviation case, compared to the Raoult's law, volume we are getting the higher. Now, when we have studied about the negative deviation, the volume we are getting the lesser than the ideal solution. Means here the maximum boiling azeotropes, it's shown by large negative deviation one. The liquids which show the large negative deviation will show the maximum boiling azeotrope. So now it shown by minimum boiling azeotrope, it's shown by large positive deviation one. The one which shows large positive deviation will show the minimum boiling azeotropes. Clear? With the help of the graphs, now I will make you clear. Now you listen. First we are going to study minimum boiling azeotropic mixture. So listen carefully to the graph. Now reading of the graph is very, very important. Now what I said, through the fractional distillation I can separate out what I can separate out? I can separate out the which one? Azeotropic mixture and the pure one component. These are the some experimental graphs they have given through the fractional distillation. Fractional distillation means, now here I was taking the one azeotropic mixture. Now after taking the azeotropic mixture, done. Clear? Now this is a azeotropic mixture. In this azeotropic mixture, when it has been converted into the gaseous, clear? Now here you can see this is a azeotropic mixture, mole fraction. Now if you take the one component air, and if you take the one component B here, one component A and one is the component B, one component A and the one component B you have taken. Clear? Now whatever we are having here, it is a which one? This is P naught A. Whatever we are having here, it is a P naught B. Now vapor pressure of the P naught B is higher than the vapor pressure of the A. Vapor pressure of the A. Now how to read the graph? Now you see here, at some particular pressure, at certain particular pressure, at particular pressure, if I talk this pressure I was talking, in this pressure it is cutting the liquid composition curve, right? Liquid composition curve. In this liquid composition curve, here this is a liquid composition curve. In this liquid composition curve, let's suppose we are taking the A and B. One A and B we are taking. One A and B we are taking. In this liquid composition curve, mole fraction of the A is, let's suppose, 0.7. Then mole fraction of the B is how much? 0.3. Mole fraction of the B is 0.3. This liquid has been converted into the gaseous, right? This liquid has been converted into the gaseous. When this liquid has been converted into the gaseous, at the same vapor pressure, at the same pressure, if you want to calculate, now this is cutting its vapor curve, right? This is cutting its vapor curve. It is cutting its vapor curve. Now in this vapor curve, this is the vapor curve. This vapor curve, whatever the vapors it has came, here the richer in B. It is richer in B. Means more B will be there, because mole fraction of the A is higher, means mole fraction of the B in the liquid phase, if it is less, means more the B will be here, right? More the B will be here. Means if the 10 B gaseous molecules, if it is there, means only 2 A gaseous molecule will be there. Only the A gaseous molecule will be there. Now what I was doing, this mixture I was condensating. What is the meaning of the condensation? Making the gaseous into liquid. When this gas is condensating, and it will be converted into the another component, another one component it has came. Let's suppose this is a one component. Now this is a 2 component. Now from where we have, from this A and B, we have first converted into the gaseous. After converting into the gaseous, we have condensated it and we have brought it into the compartment 2. Now this compartment 2, again it will be converted into the vapors, right? Again it will be converted into vapors. Then when this gaseous, when it has reached to the compartment 2, what is the mole fraction? What is this mole fraction of this liquid in the compartment 2? I want to calculate. Now you see. So this gas, let's suppose you take it this as a X. This gas you take this as a X. This X gas only condensated and came into here, right? This X gas only, it has condensated and it is came to here. Then what is the mole fraction of this one? Means, see the mole fraction of this one, this gas, when it has converted into the liquid. Now in this liquid, the composition curve is this one, right? This is a liquid composition curve of the X. This is X vapor. When it has reached to the compartment 2, I want to calculate its mole fraction in the liquid phase. So this liquid X in the mole fraction in the liquid phase, if I want to calculate, now this is a curve. This is a curve. Means you see the mole fraction of the X, and this X when it has converted into the liquid and when it has reached into the compartment 2, the mole fractions are same, right? You can see mole fractions are same in the liquid phase and the gaseous phase. Mole fraction is same. Then again I was condensating this one. And I was made it into the compartment 3. And again I want to make it into the compartment 3. This liquid, when it has converted into this vapor, this vapor, how much vapor pressure it is having, how much mole fraction it is having, I want to calculate. This liquid above, some gases are there, right? This gaseous vapor pressure is how much? Now you see, this is liquid X. This is a liquid X. This is a liquid X. This is a gaseous X. Now, this liquid X, when it has converted into vapor, from where I can calculate? From here I can calculate. From this graph I can calculate. Now, this is a liquid X when it has converted into vapor. Now, it's from here I will get. Again, when it has converted into the liquid, it has reached to the component 3. When it has reached to the component 3, again it will be converted into gaseous, right? Fractional distillation, like that, one by one we have to distill it. See, above it's liquid. When it has converted into this gas, again it will be converted into the liquid, right, in the component 3. If you want to calculate, here you will get the vapor. From here, again if you go, you are reaching to the azeotropic mixture. Means either we can separate out the pure azeotropic mixture. If you go it from here, we are getting one pure component of the A. If you go the graph in this manner, we are getting the azeotropic mixture. If you grow the graph in this manner, we are getting the pure component A. Clear? Through the fractional distillation, either we can get the azeotropic mixture, either we can get any of the A or B. Either any of the A or B we will get. This is the graph on the basis of the vapor pressure. Now you see, if the graph, if they have given on the basis of which one? Boiling temperature. If they have given the graph on the basis of boiling temperature, now how to read the graph? Now you see, now at this temperature, now same thing again, this is a liquid. Now here the boiling temperature of the B is less, means in the gaseous phase B will be the more richer, right? Now you see, at this temperature, liquid composition is this much. Means here if it is A and B, if I say, here the mole fraction of the A is 0.7. If it is 0.3, if you got it here, means A should be more, right? So 0.7. Now the same, if I want to calculate this liquid above gas mole fraction, I want to calculate. Extend the graph. Then this is a vapor composition curve, right? This is a vapor composition curve. Now if you want to calculate here, this will be the vapor composition curve it is giving. Then again you are condensating. Into the which one? You are condensating into the new liquid. This is something X you take. Now this is a X dash is a liquid. X dash in the liquid and the X is in the gas. Then this gas, when it has converted into the liquid, how much mole fraction it is having? So draw the graph in this manner. Now this liquid X, when it has converted into the liquid, its mole fraction will be get it from here. Now this is a X dash. Clear? Now you see, compartment 1, liquid above the gaseous mole fraction, when we have condensated and when we have passed it into the compartment 2, this condensate and this gaseous vapor, mole fraction is same, right? Now you can see the mole fraction is same here. Both the mole fraction is same in the liquid phase and the vapor phase. Again from here, when it has converted into the gaseous, if you want to calculate its mole fraction in the gaseous phase, means from here you will get. You can see, from here you will get. Now in the liquid phase you will get it here. From the gaseous phase you will get it here. From the liquid phase you will get. From, if you reach it here, what you are getting? This is azeotropic mixture. Means if you go it from here, either we are getting the azeotropic mixture. Now if you go it from here, either we'll get the pure A. Either we may get the pure one component or azeotropic mixture, but we cannot separating out both the pure A and the pure B, right? We cannot separating out. Either we can separate out through the fractional distillation, either we can separate out the azeotropic mixture, either we can separate out the which one? Either we can separate out the which one? Any of the pure component or any azeotropic mixture. Clear? Now this is about the azeotropic mixture. So now here what we are going to see, what are the some general example that it is going to form the azeotropic mixture. What are the some general example which are going to form the azeotropic mixture, and which one will form the maximum boiling azeotropic and which one will form the minimum boiling azeotropic, we'll see. First one, the examples for the minimum boiling azeotropes. These solutions will form the minimum boiling azeotrope. Already I said you what, the one which shows the large positive deviation will show the minimum boiling azeotropes. Minimum boiling azeotropes it will show. Example, H2O plus ethanol if you add. H2O plus ethanol if you add. Normally H2O boiling temperature is 100 degrees Celsius. Now ethanol boiling temperature is how much? 78 degrees Celsius. 78 degrees Celsius. Clear? Now when these two has formed the azeotropic mixture, this mixture boiling temperature is somewhat 77.9 degrees Celsius. Somewhat 77.9 degrees Celsius. That's the reason this H2O plus ethanol we will call it as a minimum boiling azeotropes. Compared to these two boilings temperature, it is boiling below to its two temperatures. It's below to its two temperature. Okay. Now maximum boiling azeotropic mixture. Maximum boiling azeotropic mixtures will be shown by example, that is well known example for you, that is H2O plus HCl. I was taking H2O plus HCl. Now H2O boiling temperature in the Kelvin, it is a 373 Kelvin. Okay. Now here HCl boiling temperature is 118 Kelvin. Clear? Now these two are forming the one azeotropic mixture. When these two has formed the azeotropic mixture, this mixture is boiling at the temperature of 383 Kelvin. Clear? 373 and 118. Compared to these two solutions boiling temperature, it is boiling at the higher temperature, right? That's the reason maximum boiling azeotropes. Only one thing you remember. If you want to see about the graphs of the maximum boiling azeotropes, graph will be in this manner. Maximum boiling azeotropes, see, minimum boiling azeotropes graph is one is above. Clear? Now maximum boiling azeotrope graphs will be in this manner. Same thing again here also, same thing. Clear? There is somewhat difference between the minimum boiling azeotropic mixture graph and the maximum azeotropic mixture graph. These are experimentally given. Okay, these graphs are experimentally given and we are studying about it. Clear? This is about the azeotropic mixture. Okay, and see you in the next lecture.